Chapter 24, Probability and Statistics, Section 24.4, Boltzmann Distribution. The mathematical expression of the Boltzmann distribution is this: AI over AJ is equal to E to the power of negative energy difference over kBt. A sub I is the number of particles that occupy the energy level I. A sub j is the number of particles in energy level j. So the ratio between AI and AJ is the ratio between these two exponential functions, e to the power of negative epsilon I slash kBt over e to the power of negative epsilon j over kBt, the ratio between these two. So essentially, the number of particles is proportional to the exponential function of negative energy over kBt. The Boltzmann distribution is the most probable distribution when the number of particles n and the total energy E of the system are held constant. The proof is as follows. If n particles occupy various energy levels, the total number of microstates W is this. W is n factorial over A1 factorial, A2 factorial, A3 factorial, etc. W may be viewed as the number of permutations of n particles, that's n factorial, but among which the permutations of A1 particles are indistinguishable. So if we have, for example, 5 particles in energy level 1, well, that's just one arrangement. So we need to have this n factorial over A1 factorial. So whether you have A, B, C, D, E in energy level 1 versus B, C, D, A in energy level 1, it's the same thing. We need to look at every single energy level. Therefore, the expression is this: it's n1 factorial over n2 factorial, n1 factorial, n factorial over a1 factorial, a2 factorial, etc. This denotes product. So this is just the product of all those factorials. Now, when the number of particles and the total energy E are held constant, to maximize W, within these two constraints, we can choose to maximize the natural logarithm of W for convenience. The natural logarithm of W is the natural logarithm of n factorial over, on the bottom, the product of all those factorials, and therefore it's just the logarithm of n factorial minus the sum of the logarithm of AI factorial. Again, we have two constraints. The first constraint is the total number of particles must be n. The second constraint is this: the total energy must be E. N is a constant, E is a constant. Now we define the Lagrangian L with these two constraints. The Lagrangian L is defined to be the natural logarithm of W, the number of microstates of the most predominant configuration, minus alpha times the first constraint over here. This is 0 always, minus beta times this constraint, always it's 0. Alpha and beta are called Lagrange multipliers. Now let's optimize this Lagrangian. How do we do this? We just need to take the first derivative of this Lagrangian with respect to A1, A2, A3, A4, etc. Again, this Lagrangian is Ln n factorial minus the sigma of Ln AI factorial, because W is n factorial, divided by the product of A1 factorial, A2 factorial, etc. So we have this from Ln W over here. And then we copy the two constraints here and here, multiply by this Lagrange multipliers, alpha and beta, and we set dl over dA1 is 0, dl over dA2 is 0, etc. So first, dl over dA1 is 0. So over here we have dl on top, dA1 on the bottom. How do we evaluate this? Well, first we need to remember n is a constant. The total number of particles is a constant. The total energy is a constant. So when you see uppercase N, when you see uppercase N here, and when you see E here, we can drop them. They do not depend on dA1. So we have this simplified expression over here. So this goes in here, this part goes in here, and it's dropped, and this part goes in here. Alright, and also because N2 is independent of A1, A3 is independent of A1, A4 is independent of A1, etc., etc. So when we look at this sum, only one term in this sum depends on A1. That is this. Only one term in this sum depends on A1. Only one term in this sum, a series of terms, only A1, epsilon 1 depends on A1. So we further simplify the expression to here. Now it's really simple. I have only 1, 2, 3, only 3 terms. By maximizing the Lagrangian, we get this equation. We can just evaluate this derivative, and this derivative. It's a little tricky to evaluate the derivative of the logarithm of A1 factorial. We need to use Stirling's approximation. Well, Stirling's approximation is this. The natural logarithm of x factorial is approximately x times Ln(x) minus x when x is large. So we can just simply use this approximation. We say Ln A1 factorial is A1 times Ln A1 minus A1 over here. And then we can just evaluate those integrals easily. Over here we use the product rule. It's Ln A1 plus A1 times 1 over A1, which is 1, and then minus 1 over here. And then this is just simply alpha, this term, okay? Negative alpha times A1 over dA1 is just negative alpha. Over here it's just negative beta times epsilon 1. We get this expression. 1 and negative 1 cancel, so we have Ln A1 is just negative alpha minus beta epsilon 1. It's pretty simple. See, we got a nice equation for A1. A1 is expressed as in terms of alpha and beta, and it does depend on epsilon 1. You can see that we can derive similar equations for A2, A3, A4. Now we prove Stirling's approximation. This is true when x is large. So first, Ln(x) factorial is the sum of Ln1, Ln2, Ln3, Ln4, Ln5, all the way to Ln(x). And the sum of Ln(x) is roughly the integral of Ln dn. So look at here. The integral of Ln dn is the area below the red curve. The red curve is Ln(x), all right? And what about those bars? Those bars are Ln1, Ln2, Ln3, Ln4, Ln5. All right, the height of the bars is Ln0, Ln1, Ln2, Ln3, Ln5, Ln4, Ln5, etc. So if you look at the area of the bars, it's Ln0 times 1, Ln1 times 1, Ln2 times 1. So if you sum up all those bars, it's going to be the sum of Ln(x) over here. Alright, and by just looking at this, the integral of the red curve is approximately the sum of the areas of all the bars, right? If you sum up all the bars, approximately this sum is going to be roughly the integral value, which is the area under this red curve. So we have this approximation, and we just need to know what's the integral of Ln n. It's n times Ln minus n. We plug in all those values, we get this. And then finally we make a little bit approximation, we get this. Ln(x) factorial is roughly x times Ln(x) minus x. We can verify this with some numerical examples. Let's say x is 10,000. The logarithm of 10,000 factorial is 82,109. And then we look at the approximation, 10,000 times Ln 10,000 minus 10,000. Well, it's 82,103, so you can see this too. Well, differ by only roughly 5 out of 80,000. It's a small percentage error. It's a very small percentage error. So that's why we can use the Stirling approximation here. The logarithm of A1 factorial is roughly A1 times Ln A1 minus A1. So that we can evaluate this derivative and we get this nice relationship. A1 can be expressed in terms of alpha and beta, and later we'll see we can express A2 in terms of alpha and beta similarly. So again, keeping this Lagrangian, we maximize Lnw with two constraints here and here, multiplied by the Lagrangian multipliers alpha and beta. And we have different equations to evaluate dl over dA1 is 0, dl over dA2 is 0, dl over dA3 is 0, etc. When we use Sterling's approximation, we can simplify this part, and then we can evaluate dl over dA1. This should be 0, and we got this equation. The logarithm of A1 should be negative alpha minus beta times epsilon 1. A1 is expressed in terms of alpha and beta. Similarly, A2 can be expressed in terms of alpha and beta. Just exactly same derivation. Instead of doing the derivation for energy level 1, we just do the derivation for energy level 2, we get this equation. And similarly, we get other equations for energy level I, energy level J. So you can see the expression is this for AI, the expression for this, for energy level J. Now, we take the ratio between AI and AJ. AI over AJ is e to the power of negative alpha times e to the power of negative beta epsilon I over a similar expression with level J here, and e to the power of negative alpha, e to the power of negative alpha cancel. We get this. What is this? Actually, this is Boltzmann distribution. Now, what is beta? Experimentally, we can measure the populations in various energy levels for a constant NE system and obtain the value of beta. So for example, if you know this energy level, you know this energy level, and if I know there are 200 particles here in this energy level, 500 particles in this energy level, we plug in all the numbers, and then we solve for beta. It turns out beta is 1 over kBT, and the kB is Boltzmann's constant, T is the temperature. The value of kB is exact. kB is actually the ideal gas constant over Avogadro constant. The value of kB is 1.380,649 times 10 to the power of negative 23 joule per Kelvin. I think this is UPAC definition or NIST definition, I forgot, but this is the exact value. Again, R is the gas constant, N sub A is Avogadro constant. So you can actually get the value of R by multiplying this with Avogadro constant, I think, which is 6.02214076 times 10 to the power of 23. So, and then you get R. The mathematical expression of the Boltzmann distribution is this. Again, AI over AJ is the ratio between these two exponential functions, e to the power of negative energy over kBT. This is the energy of the ith energy level, this is the energy of the jth energy level, and then we can combine this two. It's e to the power of negative energy difference over kBT. The higher the energy, the smaller the occupation number. Again, A sub I is the number of particles that occupy the energy level I. So A sub I is the population or the occupation number of energy level I. Here, let's study a numerical example. Consider a collection of 900,000 particles that occupy 3 energy levels, 0, epsilon, 2 epsilon. What if the total energy is 400,000 epsilon? And then let's compute the maximum number of microstates associated with the single predominant configuration. We have two constraints. N1 plus N2 plus N3 has to be 900,000. This is the total number of particles. Now let's look at the energy. Well, N1 particles, they have 0 energy. N2 particles each has epsilon. N3 particles each has 2 epsilon. So we have another constraint over here. And now let's just do it. N1 is simply 900,000 minus N2 minus N3. N2 is simply 400,000 minus 2 times N3, etc. We get these two equations. And we can then express N1 in terms of N3, and then W should be N factorial on top. And then N1 factorial, N2 factorial, N3 factorials on the bottom. And now we have the expression of ln W. W is the number of microstates. Alright, this is the expression of ln W in terms of only one variable N3. How do we maximize this? Well, the first derivative of ln W should be 0. So we take the first derivative. We do need to use Sterling's approximation. If we take the first derivative of ln x factorial, We expand this into x ln x minus x. Well, this is Stirling approximation from the logarithm of x factorial to x times ln x minus x. And the derivative of x times ln x is very simple. It's ln x plus x times 1 over x, and then minus 1 over here, we get ln x. So the derivative of the logarithm of x factorial is simply ln x. And then we can just simplify this expression. We get this minus 2 times this plus this. It's just 0. And it's a very simple equation. It's simplified to a quadratic equation that we can solve. All right. So mostly it's just this term divided by this squared multiplied by this should be 1. Alright, that's just typical logarithm operation. How do we solve this? Well, it's just a quadratic equation. You can solve it by yourself. I used the Wolfram alpha. I got the values for n3. It can be this, it can be this. It cannot be this, because if you get this, then the value of n2 is going to be negative. That's unphysical. You cannot have a negative number of particles in energy level 2 or any other energy levels. You cannot have a negative number of particles. So n3 has to be 87,000, and then n2 is this 225,000 ish, and n1 is 587,000 ish. Now we calculate the ratios between those occupation numbers or populations. N2 over n1 is 0.385, n3 over n2 is also 0.385. These two ratios are exactly the same. Is this a coincidence? No, it's not. Well, this is an example of the Boltzmann distribution when two energy spacings are the same. When you have two energy spacings and the two ratios are the same. The temperature of the system is proportional to epsilon. The proof is very simple. N2 over N1, N3 over N1 is simply e to the power of energy spacing or energy difference over kBT. So between the three energy levels, 0, epsilon, and 2 epsilon, well, the energy spacing is just epsilon. So we have this equation, and this equation, e to the power of negative energy difference over kBT, should be the ratio 0.385, and then we solve this equation. We get temperature is equal to epsilon over 0.9545 kb. Alright, so if you know the value of this epsilon, you can compute the temperature. If you are given temperature, you can compute epsilon. The total number of microstates of this predominant configuration is this. We have 900,000 particles in total, so that's 900,000 factorial on top. We have three occupation numbers in the first, second, third energy levels. 0, epsilon, 1 epsilon, 2 epsilons, and then we can compute W. W is huge. W is 10 to the power of 332,855. It's a huge number over here. This is W. That's the number of microstates associated with the predominant configuration with two constraints. The total number of particles is 900,000. The total amount of energy is 400,000 epsilon. Using the number of microstates, assuming the Boltzmann distribution among the three energy levels, we have the Boltzmann entropy. The Boltzmann entropy is just K sub B times the logarithm of W. So over here, we use the number of microstates associated with only one configuration, the predominant configuration. With this many microstates, we take the logarithm of W, we get this many kb. Of course, you can plug in the value of kb to get the value of entropy, but let's not do that. Let's just use kb as the unit of entropy. It's just more convenient. The total number of microstates of all possible distributions. What if we assign 400,000 quanta of energy to 900,000 particles? What's the exact number of microstates? We're going to use this formula. We learned this formula before. We will prove this formula later. The total number of microstates is this: the number of energy quanta plus the number of particles minus 1. factorial. On the bottom, the number of energy quanta factorial, and the number of particles minus 1 factorial. So we can do this. We get 10 to the power of 348,000. Using the total number of all microstates associated with all configurations, we get this entropy. Now let's compare this entropy from the single predominant configuration. This is the entropy from all configurations. What's the difference? Well, this divided by this, we get 95.5%. It's not too bad. It's not too bad. So for this example problem, if we use just one single configuration, the most probable configuration, the predominant configuration, we can recover 95.5% of the total entropy. There is 4.5% error, and this error is mainly due to the particles being restricted to have only 2 epsilon or 1 epsilon or 0 epsilon. So what if we allow all those particles to occupy even 3 epsilon, 4 epsilon, even 400,000 epsilon energy level, and then calculate the entropy for the most probable configuration or predominant configuration, and then we will be able to get a value extremely close to the exact entropy. Now let's do it. Let's use the method of Lagrange multipliers to study this similar numerical example. But this time we will allow those particles to occupy higher energy levels. We will allow the particles to be in an energy level of 3 epsilon, 4 epsilon, 5 epsilon, or even 400,000 epsilon. So you can indeed have one particle in this energy level, and all other particles with just 0 energy. Now again, we have constraints here. The total energy is 400,000 epsilon, and the total number of particles is 900,000. We define a Lagrange here. L is Ln(w) minus alpha times the first constraint for the number of particles minus beta times the second constraint regarding the total energy. The number of microstates is this, n factorial over a0 factorial, a1 factorial, a2 factorial, a3 factorial. So over here, a0 is energy level with 0 energy, a1 is the energy level with 1 epsilon, 2 epsilon, 3 epsilon, all the way up. Actually, it's not infinity here. It should be 400,000. I put infinity here. It's not wrong because simply in this energy level of 1 billion epsilon, the occupation number is just 0. 0 factorial is 1 anyway. It's not going to affect the value of this. So this equation is also correct. Now A sub I is the number of particles that occupy energy level I. A sub I is also called the occupation number. A sub I is also called the population in energy level I. Now the Lagrange is this. Alright, we plug in the number n is equal to 900,000 and E is 400,000 epsilon. So we need to set dl over dA0 is 0, dl over dA1 is 0, dl over dA2 is 0, etc., etc. Alright, we're going to do all this. Alright. And then we have this equation. Remember, we can simply use Stirring's approximation. Ln AI factorial is AI times Ln AI minus AI. Alright, so we can also, because A2 does not depend on A1, A3 does not depend on A1, A4 does not depend on A1. So when we are doing this, this is the first derivative of a sum. We can just look at one of the many terms, just the A1 terms. It's going to be here. All right, this is going to be here. We have this equation, and then we use Stirring approximation. I think this derivative is just the logarithm of AI. This is easy. We have the first derivative of a sum, and among all those terms, there's only AI term that depends on AI. Also over here, among all those terms in the sum, only AI epsilon I depends on AI. So the derivative is epsilon I. So those are just mathematical kind of just operations. Let's just work on it. Let's do dl over dai. Again, out of just the many terms in a sum, only one term depends on AI. So we have this depends on AI, this depends on AI, this depends on AI. And we use Stirling's approximation, which is this. The logarithm of x factorial is roughly x times ln x minus x. So we can evaluate this dl over dai. This part is pretty simple. It's going to be just ln ai with a negative sign in the front and the minus alpha minus beta epsilon I. So we got this equation. And in general, a sub I is e to the power of negative alpha times e to the power of negative beta times epsilon I. The total number of particles is 900,000, so the sum of all those occupation numbers should be 900,000. This looks really complicated, alright? The sum of e to the power of negative alpha, e to the power of negative beta epsilon I is 900,000. To simplify this, we have some tricks. We will set q to be the sum of e to the power of negative beta epsilon I. So we do this. Alright, so when we do this, honestly, this q has physical meaning in physical chemistry. It's called partition function, but it's going to be introduced in the last chapter. So for now, we'll just say, well, q is the sum of those exponential functions. Alright, e to the power of negative beta epsilon I. So I is from 0 to infinity. Alright, so we have the expression of q here. And once we have the expression of q here, you can see, given this equation, you can see e to the power of negative alpha. Alright, this term does not contain I because, it's just alpha, the Lagrange multiplier. I can take this out of the sum. So this sum is e to the power of negative alpha multiplied by the sum of e to the power of negative beta is epsilon I, which is just q. Alright, remember, e to the power of negative alpha, we take it out. Alright, e to the power of negative alpha, we take it out. It times this sum is n. And that sum is just defined to be the q, partition function. Alright, so e to the power of negative alpha is n over q. Again, q is the so-called partition function in statistical thermodynamics. Now, a sub I is simply just n over q times e to the power of negative beta epsilon I. So how do we get this? Well, over here, you can see, a sub I is e to the power of negative alpha times e to the power of negative beta epsilon I, and e to the power of negative alpha is what? It's n over q. So this is n over q, this is n over q, this part is n over q. Alright, so a sub I is n over q times its exponential function over here. And we can evaluate this q. Q is the sum of many exponential functions, so we can expand this sum. It's 1 plus e to the power of negative beta epsilon, e to the power of negative 2 beta epsilon, because we have 2 epsilon energy. In that energy level, e to the power of negative 3 beta epsilon, etc. Now, how do we evaluate q? Well, both sides can multiply by this. Same thing, alright? So we have q multiplied by this, and all this multiplied by this. So on the left-hand side, it's q multiplied by this exponential function. On the right-hand side, it's this exponential function multiplied by a sum, which is 1 plus e to the power of negative beta epsilon plus e to the power of negative 2 beta epsilon, etc. So let's do this multiplication. We get this. Let's do this multiplication. We get e to the power of negative 2 beta epsilon, and then e to the power of negative 3 beta epsilon. Now let's examine this the sum here. Look at this sum. This sum is mostly just this sum, except 1. So this whole thing is simply this q minus 1. Alright, now this is a trick. E to the power of negative beta epsilon times q is simply q minus 1. Alright, so now we have this simple equation. E to the power of negative beta epsilon times q is just q minus 1. So q is just 1 over 1 minus e to the power of negative beta epsilon. So we get this expression of q, and before we have a sub I is n over q times e to the power of negative beta epsilon I, and then we can replace this q with 1 over 1 minus epsilon e to the power of beta epsilon, and then a sub I. The occupation number of energy level I is the total number of particles times e minus e to the power of negative beta epsilon, and then times e to the power of negative beta epsilon I. Epsilon I is the energy of the ith energy level, and over here this is the reciprocal of q, and we get a nice equation for the occupation number. Again, Q is defined to be the sum of e to the power of negative beta epsilon I. This is by definition. Q is called the Pachin function. dq over d beta, we're going to evaluate this, is the derivative of the sum. The derivative of the sum is the sum of the derivative. That's just calculus. And now let's take this derivative. It's simple. It's the exponential function. It's itself multiplied by epsilon I with a negative sign, because you need to use the chain rule to take the derivative of negative beta epsilon I with respect to beta as well. It's negative epsilon I. And then also you copy the exponential function over here. Alright? Why do we want to do this? Well, this is related to the energy of the system. Let's see. The total energy of all these particles, well, we know it's 400,000 epsilon. Now let's do some derivation. The sum of AI epsilon I is the total energy. And we know A sub I is n over Q times this exponential function, e to the power of negative beta epsilon I. And then we have epsilon I over here, right? Look, n does not depend on I. Q does not depend on I. So I take this n over Q out of the sum. We have n over Q times the sum of e to the power of negative beta epsilon I epsilon I. I think we saw this before, right here. Okay, this is this. Alright, just with one negative sign here. So the total energy should be n over Q times this guy, dq over d beta, with a negative sign. So the total energy should be 900,000, which is the total number of particles n, over Q, times negative dq over d beta. Because dq over d beta is negative this sum. Alright, and this should be 400,000 epsilon. That's the total energy. And then we have this expression, dq over q over d beta is negative 4 over 9 epsilon. So we got this equation over here. Alright, that's kind of interesting. We got this equation. We got this equation, and we've got the expression of q. We derived this in the previous page. And now what we need to do is we just need to plug in the expression of q in here. It's going to be dq over d beta. We're going to evaluate that, and we have 1 over q. 1 over q is simply this denominator, so we copy that here, and we do dq over d beta. We're going to use chain rule. We're going to get negative 1 over this thing squared, and then we'll have to take the derivative of whatever in this pair of parentheses, which is epsilon times e to the power of negative beta epsilon. Alright? So this whole thing is negative 4 over 9 epsilon. And now we need to clean it up. Alright, we need to clean it up. It's pretty easy, because you see this expression here, and you see the same thing squared. So we'll just keep one of this, alright, on the bottom. On top, we have e to the power of negative beta epsilon, right? Negative sign cancel. Epsilon and epsilon cancel, so we get this expression. Once we have this expression, we can easily get the value of e to the power of negative beta epsilon. It's 4 over 13. You have 4 over 13 on top. You have 9 over 13 on the bottom. Alright, 4 over 13 divided by 9 over 13. You get 4 over 9. So really nice. We got this. See, if you know the value of beta, we determine epsilon. If you know epsilon, we can determine beta. Get back to this. A sub I is the occupation number. We can express A sub I as n over q times e to the power of negative beta epsilon I, and also q is the reciprocal of this. Q is the reciprocal of 1 minus e to the power of negative beta epsilon. And we even determine the value of e to the power of negative beta epsilon, which is 4 over 13 from the previous page. And beta has a physical meaning. The reciprocal of beta is kBt. And the kBt is the reciprocal of beta. And we know this negative beta epsilon is the logarithm of 4 over 13. So over here, and then we can see kBt is proportional to epsilon. In this system, kBt is 0.848 epsilon. Alright, again, if you know epsilon, you determine temperature. If you know temperature, you can determine epsilon. Now let's look at the expression of A sub I, and we can compute the occupation numbers. A sub I is this. Again, it's just this. Over here, e to the power negative beta epsilon I is simply this, because epsilon I is simply I times epsilon, right? When I is 0, we have 0 energy. When I is 1, we have 1 epsilon. When I is 2, in energy level 2, we have 2 epsilon. In energy level 3, we have 3 epsilon. So we got this. And e to the power of negative beta epsilon is 4 over 13. So we got this expression. Alright, so this is the expression of A sub I, and we know n is 900,000. We just need to plug in I equals 0 to get A0. When I is 1, we get A1. When I is 2, we get A2. When I is 3, we get A3. So we got all those numbers. Those are the number of particles in energy levels 0, 1, 2, 3, 4, 5, 6. And you can keep computing this. So I did this in an Excel spreadsheet. So when energy level 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you can see the occupation numbers decrease. And that's just the Boltzmann distribution. You know, when you have higher energy, you have a lower occupation number. All right, and the Boltzmann distribution is an exponential function. Given those occupation numbers, now we can use this equation to calculate the number of microstates associated with just one single predominant configuration. So this configuration, all right, we have in this configuration, we have maximized the number of microstates. And in this predominant configuration, we have this many particles in this energy level 0, this many particles in energy level 1, etc. All right. Now let's look at the Boltzmann entropy. It's the logarithm of this times Kb. All right. So we're just evaluate this. Unfortunately, there are so many different energy levels. So over here we compute energy level 6 over here in the graph. We computed energy level 6, 7, 8, 9, 10 as well, from 0 to 10. And okay, you can see over here the occupation number is pretty small already. So you can plug in I equals 10 over here, and A sub 10 is pretty small. And we continued to calculate it, A sub 11, 12, 13, 14, 15, and 16. All right, and then we will include the 16 lowest energy levels in this calculation. It's just impractical to include all those energy levels, so we're just to look at the top 16. So we're going to estimate the entropy this way, all right? And the entropy is the logarithm of 900,000 factorial, and then minus ln over here, this A0 factorial, A1 factorial, A2 factorial, A3 factorial. We just keep going. We all the way go to A16 factorial, and we get this much kb. All right, it's 2,440 kb. Well, you can try to include energy level number 17, 18, 19, 20. You will get pretty much the same value here. Yeah, look. This is the entropy we calculated using the number of microstates associated with only one configuration, the most probable configuration or the predominant configuration. We get this number. We computed the exact entropy before, which is 802,407. All right, so by using this formula to get the total number of microstates, all right. So this is how we get the exact number of microstates and the exact entropy for the system, with 900,000 particles and 400,000 energy quanta. Now compare these two values. This is the exact entropy, and this is the entropy from only one predominant configuration. What's the difference? Very small difference. They differ by only 0.001%. So it's really good approximation here. So later you'll see. In statistical thermodynamics, we will only look at one configuration, the most probable configuration. the predominant configuration, we will count the number of microstates for that one configuration and use that to compute the entropy of a thermodynamic system. And that entropy is awfully close to the exact entropy, with a percent error actually lower than this, because usually we have a thermodynamic system that contains more than 900,000 particles. The more particles we have, the better, the more accurate this approximation will become. Right, again, we made actually several approximations. Number one approximation, we assumed that only the predominant configuration should be considered. I didn't even look at any other configurations. Even the second most predominant configuration is not considered. Alright, we only looked at one single predominant configuration. And we make another approximation here. We looked at only the top 16 energy levels. I didn't even include energy level 17 epsilon, 18 epsilon, 19 epsilon, etc. But if you do, you still will get a number really close to this. Alright, really close to this. Number three, I think we used the Stirling approximation in our derivation. We assume the natural logarithm of x factorial is equal to x times ln(x) minus x. So we made three different approximations, but in the end we still computed the entropy of the system really accurately within a 0.001% error. So that's very impressive.